Assalamualaikum and a very good day. I'm Alif Nukman, the team leader for MechaJan-19. For today, my team and I will present on the feasibility study and system design for axial turbulence hydroelectric for Lata Kinjang new Perkampungan Budaya. Let's start with the project background. The Jabatan Orang Asli, with approval by the state government of Perak and Kementerian Luar Bandar, are formulating a possibility of creating a kampung budaya in Lata Kinjang. The project coverage on UTP's part is providing a feasibility study on an axial turbulence hydroelectric system for the kampung budaya. The project includes basic report on hydrodynamic of the river and its suitability for the system, pros and cons, and possible suggestion. The size of the power generation is from 15 kilowatt up to 50 kilowatt. The report should also consider the environmental impact of such system. Moving to the problem statement. Creating a kampung budaya requires electricity supply to power the daily lives of its locals. Acquiring electricity source from the government involves a lot of work and cost. Since Lata Kinjang is famous with its waterfall in which creates a fast-running river, clean energy from a hydroelectric system would be the best choice to power the village, meanwhile promoting sustainability. The objective of this project is to provide clean and sustainable energy for the communities that reside at Kampung Budaya in Lata Kinjang. To achieve this, an axial turbulence hydroelectric system is to be designed, which provides cost-effective energy and requires less maintenance. For the scope, feasibility study and system design for axial turbulence hydroelectric for Lata Kinjang New Perkampungan Budaya, involving concept generation, evaluation, and selection.
Hello, my name is Mr. Oleron. In this slide, I'm going to talk about the datum. There are two datum in these slides, whereby there are Pico Parka 500 and the Turbulent Hydro. For the Pico Parka generator, it's a generator that capable of generating electricity up to 500 watt by harvesting the kinetic energy from the stream with a minimum flow rate at the 0.1 cubic per second. Pico Pakai 500 is a hydropower generator that equipped with the screw turbine mounted on a foundation frame. A block plate is installed on the foundation frame facing the inflow. For the data number 2 was the Turbulent Hydro. Turbulent Hydro is a company that designed the vortex hydropower generation system, which can generate about 15 kilowatt to 70 kilowatt of electricity when the site requirements are met. This system uses a bypass system to allow water to flow into the turbine. This system is designed to generate electricity from the continuous flow of the river, hence providing enough energy for the community living nearby. Since that it will be used when developing the system, so this system is considered to be less reliable and require less maintenance during its operational time. For the design methodology, there are two parts in the slides, which was the design flow process and the Gantt chart. For the design process diagram, the process begins with define the problem with the project, whereby we discuss the problem statement of the project, and then we give a task to find a datum about the hydroelectric specification, and then the information gathering was done by to find a reliable source that can be used for our project. For example, like the flow rate of the river, a site visit are determined to determine the place to put the hydroelectrics. After that, a concept generation was done. To create that, we create a morphology chart, and then each member need to provide come out with on one individual concept for the hydroelectrics. Once it's done, the evaluation concept is taking place, whereby we need to rate every concept that has been done using weight decision matrix as our guideline. After that, we create a cat-based assembly drawing for the winner concept with the description of the concept. Lastly, we conclude our project with any recommendation for the future work. As we can see here is the Gantt chart of this project. As shown at the figure, the specific activity are done for this project. It has been said that through start dates and end date as our milestone that we must follow the date to ensure that our objectives are achieved.
Concept generation. So from the information gathering, we have obtained a datum concept to our problem, which are the subsystems that is consisted in the hydropower plant. Firstly, there is the filtration system in the top left. It is to prevent debris from the river from passing through the hydropower plant and disintegrating other components. There is also the flow rate control system, which is important to control the inlet water flow rate to match with the desired output of energy generation and prevent the turbine from overloading. It is also used to avoid flooding or overflowing of at the upper reservoir. The plant is also equipped with water tank system that is responsible for generating flow motion that would initiate and turns the turbine. The energy translation system, or basically the turbine system, is what translates the potential and kinetic energy of the water flow into rotational energy for the energy generation system to generate electrical power. The power distribution to the area and storage is then managed by the power management system equipped. After that, we move on to the morphological chart for idea generation. A morphological chart is a visualization tool for generating ideas in an analytical and systematic manner by capturing all the necessary product functionality and explore alternative solutions and combinations to achieve that functionality. And for our morphology chart, it is consisted of the subsystems that will complete the hydropower plant, and each options have their own benefits and downside. Therefore, there are multiple options brought up to create the best possible design ideas. Options for our filtration system are just a physical barrier for the debris, which come as nets or just metal grills with automated removal subsystem. Available options for our flow rate control system are just simple physical gate barrier that will control the amount of flow that goes through the system, or the amount of flow that will bypass the system into the lower reservoir, as you will see in the generated concepts later. Next, we have the water tank system. So the datum water tank system is a spiral tank where the vortex and pressure is created will initiate the turbine. Next is mini dam, where it is slightly improve the head and while maintaining a good flow rate of the system. Next is the water in hydro intake box, which works by directing the flow to the turbine. Next, we have the 4-bay tank, which increases the efficiency of and optimizing the head as the flow is directed straight to the generator rather than having drag slowing down the flow rate or any flow wastage that escapes the generator. About the selection of turbine system, optimal efficiency condition between the options are different, such as some requires high flow rate, whereas the others require high head. And the produced forces is also different. Some would have higher torque, whereas some would have higher speed. And depending on this, a suitable generator can be selected. Another factor in choosing the generator is the amount and kind of electrical power to be used by the locals there. And the same factor applies when choosing our power management system. After completing our morphological chart with potential solutions to the hydropower plant, each team member have generated concepts based on the subsystem in the morphological chart.
For my concept, which is concept 1, the water flow from upstream enters through the bypass inflow channel. Debris from the river is then filtered by the trash rack and can be pulled out using the built-in cleaner arm. The first square penstock gate will control the water intake flow rate, while the second gate is used to control the flushing rate of water out of the 4-bay tank. To obtain a desired flow rate, water is stored first in the 4-bay tank before releasing to the turbine. Water released flows through the penstock and then reaches the spiral tank, creating water vortex as water trying to exit the tank. The water then turns the Zotlo-Ether radial turbine, hence generating energy through the synchronous generator. The water safely exits the system, passing the outflow channel and ends in the downstream. Energy generated is sent to the off-grid power management system to be monitored and regulated.
For the second concept, trash check will be used to filter the debris. The gouging weir gate will be used to control the flow rate of water. Next, the forebay tank will be used to store the water entering from the bypass canal. The high flow rate created after exiting the forebay tank from the penstock will be sufficient to rotate the Kaplan turbine. This concept is ideal as this turbine specifically requires high flow rate to operate efficiently. The energy created will then be converted to electrical energy using synchronous generator. The power generated from the generator will then be distributed to the off-grid power system.
For concept 3, a mini-dam is constructed with a screw turbine installed on top of it at an angle. The idea is to create an overflow of water, causing the water to flow through the screw turbine, thus turning it. The work done by screw turbine will be converted into electricity by a synchronous generator and managed by an on-grid power management system. The opening of sluice gate will cause the water to flow under the system in case a reduction of flow rate is needed. Floating trash barrier will prevent any floating debris from clogging the screw turbine.
Hello, my name is Sylvester. Here the concept that I designed. Just like the third concept, concept 4 utilize the inclined and slanted screw turbine but with a combination of a hydro intake box where the flow can be concentrated to the screw turbine and improve the efficiency of the system. The concept also use synchronous generator for power generation and on a grid power system as a power management. It uses a wire gate behind the hydro intake box rather than having it under the water tank system like previous concept. And the cache trash filter used to prevent the debris from integrating any component on the system.
So the last concept uses the simple wire gate to redirect the bypass flow to the lower reservoir to control the system flow rate. And we have a go flow filter that comes with an automated filter cleaning subsystem, which I think is very useful for cleaning the filter instead of having a label. So next we have the power generation that is initiated by the mini dam that slightly increases the head that is good for the Francis turbine that requires an adequate balance of a good head and a good flow rate. Next, the Francis turbine will then spin the brushless DC generator, which I think we can exploit the row friction of the generator that would keep the momentum of the generator as the flow rate fluxes. And finally, the off-grid system is chosen for my concept because it can have no hassle with the electricity providers and making the system a lot more simpler, and the system is not interfered with the electricity grid.
Next, the 5 concepts generated underwent through evaluation process, allowing us to compare and determine which is the best. The evaluation process was conducted using weighted decision matrix or WDM. WDM is a tool used to compare the concepts generated with respect to multiple criteria, each with different levels of importance. Level of importance is also called as weight. To utilize WDM, we have created a set of criteria and its weight. Referring to the table shown, we have created 7 criteria with the first one being smoothness of fluid flow. The entire system relies heavily on the moving fluid, and any blockage will result in the system failure in worst case scenario, thus it receives a weight of 0.12. The second criteria is water storage capacity. In case of low natural flow rate, which is possible bad scenario, the storage capacity will determine how much of the negative effect can be reduced. It receives 0.06 as weight due to its low possibility. The third criteria is efficiency of power generation. The site have a limited flow rate, thus a high efficiency is preferred. It receives a weight of 0.12. Fourth is the reliability of power supply. It is one of the most important criteria for any energy source, especially if it is the main energy source, thus receiving the highest weight 0.24. Fourth would be environmentally friendly because the site is a tourist spot. The criteria has a weight of 0.1. Sixth is ease of installation due to the site is located in quite a secluded hill. It has a weight of 0.24. Lastly, ease of maintenance with a weight of 0.12. Any downtime for the system means that no power is generated, thus it is required to be minimal. To rate each concept, the members of this group are required to follow the 11-point scale rating guideline. The 11-point scale range from 0, which is totally useless solution, to 10, which is the ideal solution.
Concept 1, which is my concept, obtained a score of 5.32. With the smoothness of fluid flow received a 6 since the multiple passage may increase the chance of blockage. Water storage capacity also a 6 since it allows the control of flow rate but take additional space. Another 6 for efficiency in power generation due to the Zotlo radial turbine having decent efficiency. Highest score, which is 7 for reliability of power supply, because the water stored in the 4-way tank can be used to compensate in case of low fluid flow rate for a period of time which might affect the power generation. And a rating of 4 for environmentally friendly, ease of installation and ease of maintenance considering a lot of parts and space required for the system.
For concept 2, the highest is in terms of efficiency of power generation. This is because the concept uses a Kaplan turbine, which is one of the most efficient turbine due to its flexible blade. It received the lowest rating in the same criteria in concept 1. This concept also scored a high rating in terms of power reliability because of the usage of off-grid battery system.
For concept 3, the highest rating is in terms of smoothness of fluid flow because the concept does not require any bypass. However, it received the lowest rating in water storing capacity because it relies on overflow, thus any water stored cannot compensate any sudden drop of flow rate. It receives a rating of 7 in efficiency and ease of maintenance. This is because screw turbine requires low head and its component, turbine and generator, are above water. The reliability of power supply receives a 6 because it cannot operate below average flow rate. The environmental friendly receives a 6 due to no aquatic life can pass through, and a rating of 4 to ease of installation because the river needs to be diverted during installation.
For the concept 4, it's quite similar to concept 3, where the highest rating is the smoothness of the fluid flow and the lowest rating is the water storage capacity. The major difference lies in the ease of installation. Concept 4 can be built off-site and transported to the site, while the concept requires to build on sites.
So for concept 5, which is my concept, I have obtained the highest rating that falls on efficiency of power generation. This is because of the implementation of the Francis turbine. And then next is the lowest rating, however, in terms of the ease of installation, because the entire river has to be diverted during installation for the bypass route. Reliability and efficiency of power generation as well as the flow smoothness is okay, as the system occupies the whole river rather than diverting some of it from the river. However, this also makes it hard for maintenance and is less environmentally friendly, as it tremendously disrupt the whole river flow, and also because of the big excavation for the river diversion.
Finally, we were able to determine which concept is the best based on the highest total score. The score is calculated by multiplying the rating and its weight. With a total score of 5.68, concept 2 was chosen for further specification.
Now I'll be explaining about how we came up with our selected concept. Based on the morphology chart that was generated, each of our team members have came up with different design concepts. From these design concepts, we are able to evaluate these designs based on different design criteria. From the discussion that we have carried on, we have selected this concept to be suitable for our micro hydropower plant project. As observed, this is the assembly drawing for our selected concept. Our system consists of 9 parts, starting from the Tyrolean weir to the trash rack, and then to the weir gate, then to the bypass channel, to the forebay tank, and the penstock, Kaplan turbine, generator, and finally to the off-grid power system. In the next slide, I'll be further elaborating on the function of each of these parts. Now, I'll be explaining on the working principle of our system. First, the Tyrolean weir will cause the water level along the river to rise and get diverted to the bypass channel. The trash rack will then filter any debris from entering the bypass. After that, the gouging weir gate will control the water flow rate passing through the bypass channel. After passing the bypass channel, the water will then be stored at the forebay tank, which will then exit through a penstock at a high flow rate. The water exiting from the penstock will enter a spiral tank to spin the Kaplan turbine. Due to the rotation of the Kaplan turbine, the shaft connected to the turbine will spin the generator as well. From this, power will be generated. The power generator will be distributed to distribution line to the inverter, which converts the AC current to DC. The power is then stored at an off-grid battery system. These are the technical specifications for our selected concept. These technical specifications are based on technical guidelines that follows ISO standard. For example, the power generated by our generator is up to 15 kilowatts, which is what needed for our micro hydropower plant. The concept feasibility of our system is based on the practicality of each of the subsystems present. For the filtration system, the trash rack used is able to filter the debris from entering the bypass channel. Next, for the flow rate control system, there will be 2 parts that will be used, which is the Tyrolean weir and the gouging weir gate. The weir gate used is able to limit the flow of excessive water when there's a high flow within the river. Next, this weir gate is also able to withstand high hydrostatic pressure and external water pressure. Next, for the water tank system, the dimension of forebay tank that is used is able to store a large capacity of water and able to provide the demand when the need for water arises. The other subsystem that are present is the energy translation system, in which the rotation of the Kaplan turbine will produce mechanical energy, which will later be converted into electrical energy. The reason why we'll be using a Kaplan turbine is because it is able to operate at a high RPM and also will be efficient to operate at a high water flow rate. Next, for the power generation system, the generator that we will be using is able to produce up to 15 kilowatts, which is suitable for our micro hydropower plant project. Finally, for the power management system, the power generated from the generator will be stored in an off-grid power system through distribution lines. The reason we'll be using an off-grid power system because it is suitable for the geographic location of our hydropower plant.
Now on the conclusion. From our studies, we have developed a plausible system design to generate the required amount of power, considering its impact on the environment and the hydrodynamic of the river. The design is based on a combination of the conventional micro hydroelectric systems, which use screw turbine and vortex turbine. Due to power generation capacity, the micro hydroelectric system, which operates based on gravitational water vortex, is focused on more rather than the system that runs with screw turbine. With the finalized design, supported by technical standards, it is possible for the system to run based on the requirement. As for the recommendation, to create a clean energy resource based on the hydroelectric system, our team would also recommend exploring the use of screw turbine as a primary component, especially in the case where the source working fluid has a minimum flow rate of 0.1 meter cube per second. 500 meter of power can be generated continuously using the screw turbine, although evidently it should not be the main power generation system due to its low output. Moreover, due to the small size of the screw turbine-based generator, it will not require a high investment and it facilitated the transportation and installation process. This small power generator can be used to power the street lights for a rural area, thus increasing accessibility for the area and/or reducing the electricity cost. Designing, assembling, and installing of the screw turbine-based hydroelectric system should not take more than 6 months, dependent on site constraints, because its main attributes are simple and cost-effective. That is all for our presentation. Thank you.